Welcome, everyone. This is a session on big data and ArcGIS, basically being able to do large-scale geoanalytics with the ArcGIS technology. I'm impressed people are showing up on a Thursday afternoon after lunch on the party night. You must have a real interest in the topic if you're here on a Thursday afternoon, so thanks for coming. With me up here to the right is Mike Park. Mike Park is the lead developer on geoanalytics here at Esri, and my name is Eric Hull, and I'm the geodatabase development lead here at Esri. So we're going to take you through this stuff, give you some demos and all that. Hopefully you'll find it interesting. People oftentimes, we get people coming up to us all the time and saying, wow, what's this big data stuff? How big is big? Do I have small data, big data, whatever? One obvious thing, this is a fun little, these are just pretty graphics, it's not really doing much of anything, but one fun data set to play with is the New York City taxi cab data, pickup locations. Here we can see pickup locations across an entire year inside the New York City area, each of those little areas, and we actually are aggregating the data and creating little heat maps. If you look there, you can find little orange and red places on this little animation here. Not only can you just aggregate data by day, but into little small regions like 50 meter square regions, you can also do selections on the data where you can say, I just want to see the taxis every Friday between 8 p.m. and midnight. And this is going, again, through a whole year. And you can see some weeks are heavier than others. It's just kind of interesting way to visualize the data. But that's just eye candy for you guys to start things off. When people are working in this space and are trying to actually implement functionality that works in the big data space with large volumes of data, so we're talking any volumes up to tens of billions of items, really large collections of data or even larger, they have to rely upon various techniques and technologies. First is data distribution. People will take these humongous data collections, and they'll break them into smaller data sets. They'll go and shard them, and they'll distribute them across a collection of machines and storage technologies. This could be across one machine, across 100 machines, across 10,000 machines. But people, in order to maximize the likelihood of parallel I/O operations, will take these huge data sets and spread them around. Another thing they'll do is apply parallel processing techniques, where what you want to do is you can use a collection of machines, preferably where the data is stored, and you can process each of these smaller data sets on each of these machines and then group the results together across this big collection of machines to get your final result. So that's how you basically speed up these computations. Ideally, it's in a linear manner being if you have 10 times more machines, the computation runs in 10 times less time, a tenth of the time. So we always try to get the linear scalability here. We have to rely a lot upon infrastructures that are fault tolerant. Sometimes a hard drive fails. Sometimes the machine just crashes and goes down, but you don't want to have to restart your competition, or you don't want to have to reload your data. So this is one of the things that Google's and others back in the early days, when they were doing some of this stuff, they realized that fault tolerance was critical. At some of these large web scale companies that you see, they'll have failures, multiple failures every hour. You know, when you're running 10,000 machines, they will fail with a pretty regular cadence. So what you end up having to do is make copies of this partitioned data, put these smaller data sets on multiple machines. So if one of the machines fails, the data is still there and can still be utilized. One of the important things, this is a little bit different from how we used to do things in the 60s, 70s, 80s, and early 90s until the Cold War ended. Where back then we used to buy these really fancy big parallel machines. I know when I was in grad school, we were working on connection machines by thinking machines. You know, it's a big box that had 32,000 parallel processors in it. But that machine probably cost somewhere on the order of $25 million. So not many places had those machines. And when the Cold War dried up, when it ended, the ability to get ARPA money or DARPA money to fund these big machines also dried up. So what people did was they figured out how to create these infrastructures that could run across commodity hardware. You don't necessarily have to have a big server farm with all your blade servers and everything else like that. Maybe in your office, you have a collection of desktop machines, 10 desktop machines that no one's using anymore. Well, you can cluster those things together and lay down the technology stack and make them useful for these in these processing environments. So you don't have to buy fancy hardware. It can all just be commodity stuff. And all the stuff you see us running is on commodity hardware. Scalability. We need to have algorithms and frameworks that can be scaled to run on any number of machines. It can run on one machine, it can run on 5 machines, it can run on 100 machines or more. We need to have these things, these frameworks and algorithms that actually will scale. If you have a bigger problem or a bigger data set, throw more machines at it. If you have modest-sized collections of problems, you can have a modest-sized cluster. But the important thing here when we do all of our engineering and development work in this space is we develop algorithms that will scale, and we ensure that they scale. That's one of the big tricky parts with this whole effort. Now, another thing, this is funny. Gary King once said, big data is not about the data. What's really valuable about big data is not the data itself, it's actually the analytics and the insight that you can gain by processing this data. The interesting thing that we've seen over the past several years as we've been moving forward with developing technology in the space is there's a lot of people out there that went and set up the Hadoop stack and they've been pouring all kinds of information into the HDFS or some other distributed storage technology or NoSQL database, but not too many people are doing much with the data. People are still looking for guidance. They're still looking for some leadership as to what you can do with the data, especially things such as spatial data. There's not a whole lot of work going on out there, a whole lot of technology as of yet that plays in the space that does spatiotemporal analytics. You see occasional papers in academia and all that as you would expect, but you guys need real systems that will do this for you. So that's what this is all about. So you guys, many of you, most of you may already have big data. This can be data that's collected through smart sensors. Say you're an electric utility where you have those smart meters on the side of your house, those AMI devices that are actually taking a measurement every 15 minutes and then every 6 hours sending that bundle of information up to the electric utility. And that's done for every household that they service. So electric utilities collect vast amounts of data, usage data, based upon time of day readings on these smart meters. They also may have SCADA devices. These are control systems that they attach to their high-value assets out in the field, such as transformers or substations, things like that. They're sending them real-time feeds, often in a sub-second click or cadence. Then you have UAVs. We see that down on the trade show floor. A lot of people are flying UAVs around and capturing either still images or essentially taking that data to create cloud, essentially point clouds and actually 3D visualizations of everything. There's GPS telemetry data from all your moving vehicles. There's social media stuff, web logs, customer sentiment information that your organization may be gathering. There's also things like weather sensors or stream gauge measurements, or on heavy equipment, those big devices that may cost $250,000 or more, big bulldozer, big harvesters, whatever. Those things are filled with telemetry. They're generating vast quantities of data. We could talk about precision agriculture after this talk, but you'd be amazed how much data is being generated and collected in the field of agriculture every day. Then you have traditional imagery, frame cameras, drones, whatnot. So enough of that background stuff. Let's talk about big data analytics inside ArcGIS. Everything that we're going to show, everything that we're going to talk about from this point forward is technology that will be delivered this year. Okay? This is stuff that's going to go out with ArcGIS Pro 1.4 and ArcGIS 10.5. And that will be before the end of this year, okay? So this software that we're going to be talking about and will be demoed is actually, it's very close to beta right now. In a handful of weeks or so, it's going to be in beta form, right, Mike?
I hope so.
Good.
We'll see.
Okay. It will go out in beta.
Confidence.
Yes, inspiring.
Yeah.
Inspiring. Let's see. So what is big data analytics from our perspective? Well, this is the elevator pitch. ArcGIS has a new way of processing spatiotemporal data that is designed for big data by leveraging distributed analytics and storage. Basically, I took the past few slides and boiled it down. It was boiled down into one sentence. So let's talk about it a little bit more. Basically, it'll work with your existing GIS data as well as the new big data that you may be collecting. So yes, it will work with your existing data. Maybe it's not big data. Maybe it's modest data. That's fine. You can still apply the same technology to it. Basically, what you're going to do is you're going to register your data and you're going to go. And you're not required to use exotic distributed storage technology or anything like that. It's designed to perform both spatial and temporal analysis. That's an important statement. One of the interesting things that we observed when we were getting our feet wet in this domain is that large data sets, these large data sets that you see in the space, are oftentimes time-stamped with temporal information. When was this observation taken? It can be down to the second or sub-second timestamp level. So what we want to do is allow you to take advantage of that temporal component to this information. ArcGIS historically we've done some stuff with temporal data, spatiotemporal data, but it's not as robust as we need here in the big data space. So you're seeing us start to spearhead the injection of more temporal capabilities into the ArcGIS platform or stack. So you're going to see it in other GP tools and other parts of the software. We'll all be gaining from this. Basically, we want to allow you to utilize this data and understand it within the context of both space and time. You can think of these analyses operations, these tools that we're going to be providing as basically think of these tools as being like a regular GP tool, but we've taken the implementation that runs on standard sequential computing platforms, and behind the scenes, we've gutted the implementation. We've torn the implementation out, and we've replaced it with a new, much more sophisticated collection of algorithms and techniques that are designed from first principles to run across these distributed processing infrastructures to leverage your commodity hardware that you have assembled into a cluster of machines to utilize. Okay? Basically, it's all about making your big data that you have easier to use and easier to share within your organization. Okay? We don't want it locked up in a silo somewhere. So, with this project, we're adding big data analytics is basically adding to the existing analysis capabilities, analytic capabilities that ArcGIS already adds. Okay? So here, of course, we've always had the emphasis on desktop geoprocessing capabilities. Those will be augmented somewhat to support these more powerful analytics, but more fundamentally, the really new part here is essentially a new platform extension that utilizes server-based geoprocessing that's based upon distributed processing and storage. This is the big data analytics group that you see here in the middle. Now, with all that distributed processing and analytics, we also want to make it very easy and automatic for you to share the results of these analytics to other people in your organization. When you run one of these tools, it will store the result and it will automatically publish that data set that was produced as a result of the computation as a layer inside your WebGIS automatically. It'll be available through Portal to other people in your organization that you choose to share with. Okay? That's also a pretty interesting aspect of this new technology. Now, we want to allow you to solve new problems that you previously could not deal with your regular desktop machines. We want you to be able to run against data that's simply too big for a single machine. Okay, maybe you have hundreds of millions of 911 calls that you've been collecting over many years, or crime reports, or maybe you have billions of observations, tens of billions of observations of ship movements or vehicle movements that you've been collecting and perhaps ingesting into things like the big data file share, the spatiotemporal big data store through something like the Geo event. You have these big collections of data that just really don't work on a single desktop. We want you to be able to gain insight into both the spatial and temporal patterns. With this, the temporal aspect is key. You want to see how things are emerging, how things are changing with time, what trends are developing, what trends are receding. That's one of the really cool parts of with this space. And you need to be able to do it against massive collections in a scalable manner, meaning if you have bigger problems, throw more hardware at it. But we don't want to create a technology where you reach that point of diminishing returns where, you have bigger problems, but the system can't scale to keep up with it. And you want to be able to do all this work and meet your time constraints. Now, an important statement to make is that we've seen users, and we've done it ourselves back in Redlands, where we can create processing tasks that may need to run for months at a time. They're very large. I remember one organization that had a large topology of nearly 1 billion polygons that running on a standard desktop machine took about 110 days to validate that topology. That's a lot of processing, and you don't want to pull out the power cord on that machine. So what we're trying to do is we're trying to push the time dimension to the right, meaning a job that took months previously now may just take a few days, or something that took weeks can now take hours or days into minutes. We're really trying to push the curve, the time dimension to the right. We're not going out there and saying, yes, absolutely, you'll be able to do whatever crazy analytic in 2 seconds. No, we're not saying that. Some of these operations and some of the things that you'll see Mike demo, maybe they take a half minute, maybe they take a minute, maybe they take longer. But that's fine because you're actually able to solve a problem that was previously impossible. There's no way you could have solved it before. So let's talk a little bit about the collection of tools that we're going to be releasing as part of this initial release. Remember, this is the initial release. With subsequent releases, we will be growing the collection of functionality and tools based upon feedback from you guys, okay? We need feedback. We want feedback. So if there are particular areas that you want to see us pursue, let us know. But this is our best guess for the first release. Now, what we ended up doing was we argued back and forth, back in development, what's the important things that we need to provide? What's unimportant? What's important? It was one of those open-ended discussions. And then someone said, hey, wait a minute, didn't we have this discussion a few years back when we did ArcGIS Online? Yeah, that's right. Yeah, that spatial analysis online capability, we released a collection of 22, 23 different tasks that we found to be very important to our user community. So what we did was we basically took that collection of tools, minus anything related to transportation networks, and tried to implement them here inside this type of, this particular piece of technology. So we have tools for summarizing data. Some of these will be very familiar to you because they're already in ArcGIS Online. We've also added a couple tools that are actually not part of ArcGIS Online. We are not constrained to follow ArcGIS Spatial Analysis Online. We just use that for a good first, hey, here's where we want to go. Here you see a little graphic. This is essentially a web browser connected to Portal, and here you can see your feature analysis tools. This is a little screenshot of it. Well, you have your standard tools that you already have today, you can go and play with, but then there will be a new tab that contains the big data tools. So within data summarization, we see these 5 tools: Aggregate Points, Summarize Nearby, or Summarize Within, as well as new tools such as Reconstruct Tracks. Mike's going to show you what Reconstruct Tracks is all about a little bit later, or to create panel data out of your existing data. We'll go into each of these later. Now, you see at the bottom it says Time-Aware Tools. These are tools that we have added a temporal capability to where that temporal capability does not exist in ArcGIS Spatial Analysis Online. So we have not been constrained by the absence of temporal capabilities in these existing tools. We've gone and added them to these tools because it just simply was appropriate. We have other things for finding locations. We can find existing locations, find similar locations. Perhaps one of the most interesting areas is pattern analysis. Inside here, what we're going to do is we want to make sure that we are creating an actual science-based framework where we do support spatial statistics operations. Canonical spatial statistics operation is hotspot analysis, using the GETISOR GI-STAR statistic to find statistically significant areas of interest, okay? We want to know, you want to know with 95% confidence that this area is in fact a hotspot. Or maybe you need 3 standard deviations. You say, I want 99% certainty that this area is a hotspot. You don't want to rely on just heat map generation. Of course, we can generate heat maps, but with heat maps, you can make a problem look relatively insignificant by how you choose to create your renderers, or you can make it look terrible. Maybe there's red everywhere and a little bit of blue, or vice versa. You're just painting a pretty picture when you're doing a heat map. There's no scientific basis to what you're trying to communicate to the users. So that's why you want to use hotspot analysis. We know with statistical certainty that this thing exceeds some threshold. Okay? Also, you need to be able to do things such as create space-time cubes, essentially netCDF output, such that, because there are many tools already out there that will consume netCDF, including in ArcGIS geoprocessing today. There's a lot of tools that can deal with netCDF. Why not be able to aggregate your data down and create these space-time cubes such that they can be used by other tools that are outside of this tool collection that will run on reasonable sized collections of data, which generally would be what you get from generating a space-time cube with reasonable parameters. Also, you can do some proximity stuff. You can create buffers around features, as well as there's some capability for managing your data. Things such as being able to extract the data so it can be moved to other platforms. Say you've gone and identified the statistically significant, interesting data inside your data collection. Well, why not just clip that data out, extract that subportion of the data in this big data space, and move it into desktop where you have 1,000 other GP tools to run against it. You don't want to be limited by what we're providing out of the box here in the geoanalytics. You want to be able to use all the tools. Did someone? Okay. So that's what that's all about. Also, there's a join features tool, which is sort of the Swiss Army knife that lets you do all kinds of spatiotemporal attribute joins and control the system at a very flexible, in a very flexible manner. Okay, has familiar and simple interfaces. By that we mean it's easy to get started. Stuff is available out of the box. You don't have to go and publish anything at all. We have one type of interfaces are user experiences, user interfaces. You're able to run these analytic operations using the Portal web user experience. Okay, here you're just in a browser connected to Portal that has geoanalytics behind it. You can run it from a browser. You can of course run it through Pro. Here we see the feature analysis panel where we have the big data tools. The same collection of tools that you saw in the web experience is also available on the ribbon inside the feature analysis pane or panel. You guys all saw earlier this week Insights, that new web-based thing that's very BI-centric and has spatial capabilities, that very cool stuff called Insights. You can utilize this capability through Insights. That being said, maybe the job won't run in 1 or 2 seconds like most things you saw in Insights. Maybe it runs for a couple minutes, but Insights has been architected such that that goes into the list of longer running tasks and you can keep track of it on the side and see progress. And then when the data is ready, then you can use it inside Insights. There's also the other half of interfaces are developer interfaces. Because these things are all implemented as GP tools, they're available for Python developers. You can script these tools that we're going to be showing or we're actually delivering. Okay, you can do it that way. You could also use Python notebooks. This is something very cool that's been worked on, where at least in the big data community, we see a lot of people enjoying using a notebook-like experience for working through their data. And again, this will be supported in the Python notebooks technology that we're releasing. And then of course, it is service-based and it is available through a REST API. If you really feel like JSON's the greatest thing ever, you can get to it through our REST APIs. Now, with all this data, you can use your own big data sources. One thing to keep in mind, maybe your big data source is just a folder containing thousands or tens of thousands of shapefiles. Say you have a shapefile generated every hour, and over the course of a couple years, you're going to have a fairly large number of shapefiles. But they're all just taking readings of, they all follow, if they all are in a particular directory, single directory, and they all have essentially the same schema, they're all representing the same data, just different times, moments in time. You can go and register that information, register that file share that's somewhere out in your organization. And if it is a directory hierarchy, the software will go through the hierarchy and find all the folders containing interesting information that share a common schema inside each folder. Different folders can have different schemas, but you kind of get the point. So we'll allow you to treat that thing as a single logical data set inside this framework. Okay? Although, yeah, there are 10,000 shapefiles, there's really only one shapefile logically in your system. It just happens to be sharded into a bunch of little pieces. You can also attach to existing big data stores that you may have inside your organization. Now, you can also use your existing GIS data. Oh, I already have some stuff that I'm exposing through feature services. Well, yeah, we can consume that too. It doesn't have to just be special big data stores, big data file shares, or big data stores. It can be just regular GIS data. You can use that with this technology. It works with layers that are already in your WebGIS, okay? Now, here's a little diagram trying to represent at some level what the architecture is like, how the information flows through the system. It can work, as we said before, with all different kinds of data stores and whatnot. These are data stores that either are installed by and managed by ArcGIS in the portal itself. You see that on the bottom right. Or they can be data stores that you yourself manage, okay? That you're already managing yourself inside your organization. Now, looking at the user-managed data stores, we have enterprise. These enterprise data stores are things like Oracle, SQL Server, maybe HANA in the future. They're used to store your business and your geodata. We also have the big data file shares that we were just talking about. These are folder hierarchies that can contain hundreds, thousands, tens of thousands of shape files, or text delimited files, CSVs, tab delimited files. Whatever the delimiter is, we can address that. That we assemble them all and use them logically as one large data set. You can have big data stores. These are, maybe you have Hadoop somewhere in your organization, and you've been pumping data into HDFS. We can accommodate that. Then we have user or ESRI managed data stores. We have the relational data store that was shipped with Portal a couple releases back. That's sitting on top of Postgres. And then we have the new spatiotemporal data store that was released with 10.4 that actually is sitting on top of Elasticsearch, okay? So you can work with all those different data stores. It'll read from all of them, put it into the cluster. Okay, your server cluster starts chewing on it. And then it prepares a result. When the result's ready, it writes it back by default to the spatiotemporal big data store. It persists the result. And then it will also automatically publish these things as new WebGIS layers that are then available for people that are working with your portal. So then you can have all your other different types of client apps, such as your WebGIS layers that are connecting to Portal. You can use ArcGIS Pro, you can use Insights, you can use your Python notebooks, or you can use your REST API for consuming those published WebGIS layers that were as a result of the analytical processing that you just did. Okay? It's done automatically. So, enough slides. That was killing me.
What? Oh, sorry.
I think I killed some of them too.
I was on Twitter.
Yeah, sorry. Doing important things, I'm sure.
Yep.
Vital information.
Okay.
Here. Okay, looks good.
Good to go?
Yep,
okay.
You're good.
Oh, that kind of scaled differently than I was expecting. All right, let's zoom out a little bit. So this is one of the data sets I'll be demoing. What this is FAA Flight Data. It's 17.5 million points. It is stored as a CSV in our cluster. And as you can see from this, you can't really get any patterns from this at all. Like, this doesn't really tell you anything. Big data is hard to draw at this scale, but even if you can draw it, it's very dense, and you still just can't figure out what's going on. Except, of course, what is that, Area 51 right there?
It really is.
Yeah.
Spooky.
There's a couple of flights that go through it. We assume those were UFOs. So this data set I have registered with my server. There's a registration process that you basically point to a directory, and underneath that directory is a bunch of subdirectories, and each one of those represents a data set. You showed the Lightning data set. So it was like the Lightning data. Oh, do you have?
That'll be later on.
But how it was structured.
The Lightning data set?
Never mind.
Yeah. It was shape files inside a folder. Now I see what you're saying.
Were you even paying attention to yourself?
No, I wasn't listening to myself.
Because I zoned out.
I was just
for sure.
yammering on and on.
So underneath those subdirectories could be collections of CSVs, delimited files, shape files, and logically those are one data set to us. And the reason you get collections like that, some of you may know, some of you may not, is say you're streaming data in, you may get a day's worth of data and just push it to a directory. So you may have 20 CSVs representing 20 days of data. And we will see that as one data set, and we'll process it all at once. So what I'd like to do with this FAA data is I'm going to do a big space-time join. This is going to run on our cluster in Redlands, so there's a lot of potential for failure because I'm VPN'd in, and there's all kinds of reasons. So if it does work,
yay,
everyone will clap.
What could go wrong with this idea?
All kinds of things. All kinds of things. So I'm going to look for planes that fly near each other in space and time and altitude. And so what I'll do is I'll do a big space-time join where I'm looking for planes that are near, within maybe a mile, and in time maybe a minute, and you'll see points that are actually clumped together while they're flying, usually across the Atlantic, long-haul flights when they fly across the... Is that true?
Yeah.
Am I just making this up?
No, there are corridors.
So just like that.
And they have a certain vertical separation as well. What are you looking for?
1,000 feet?
1,000 feet, that's a typical separation
Yeah.
on a transatlantic intercontinental flight.
So this is Pro. Pro is connected to a portal. This portal is enabled for geoanalytics. And at the time you enable it for geoanalytics, you'll get a feature analysis with a bunch of big data tools. They have a little cloud, which means fast or something. All of these tools will run distributed in the cluster. They can all access these big data file shares or the big data stores that Eric was talking about before. So we'll hit the Join Features tool. And this works with stuff that's in your portal content. So we'll click on Portal Content, My Content, and we'll wait for it to load. And while it's loading, I might do something else. So I'll sign into the portal as admin, of course. And we'll look at my content. You guys can see that okay? Perfect.
Yeah, nice and big.
I do. And you can see that our big data file share is actually a item in Portal, and we can access this. And this worked. Good. Step one. So I have this FAA data set. You can see its points. I've got some other data sets, Uber, tracks, hurricane tracks. We're going to go over some of those in the next demos. So what I do here is we have a target layer, and we have a join layer. And I'm actually joining the FAA data with itself. So it's both the target and the join. We'll specify an output name, call it FAA near. This is what the feature service is called after the result is created. So you'll have a feature service in your portal hosted that's called FAA near. I'm going to get rid of that so we have more space. So we choose our spatial relationship. Anybody that's familiar with the spatial join tool in the traditional desktop GP tools, you can specify near, contains, intersects, any of that. And we're going to say we want a spatial near distance of 1 mile. Now, we can also specify a temporal relationship. So if your data set was registered with time, maybe you have a timestamp in there, maybe you have it split across year, month, day, any type of registration of time, we can work with the time as if it was, it's basically at the same level as geometry. So features traditionally are attributes in geometry. For us, they're attributes, geometry, and time, where time could be an instant or an interval, could be a range of time. So we'll choose a near temporal relationship of 1 minute. You can also specify attribute relationships. So you could say the target, aircraft ID equals the join aircraft ID, which we're not going to do, but you could. And then one final step is this join condition. This is a free-form expression that gets applied after the spatial and temporal relationships are calculated. Now you have an expression that you can apply to further filter it. So what our expression says is that the target altitude minus the join altitude is, the absolute value is less than 10. 10 meaning flight level, it's actually 1,000 feet. So we're looking for planes that are actually near each other in altitude, within 1,000 feet. Okay?
Basically looking for all the near misses.
I didn't say that.
I did.
We're not looking for crashes.
No, I said misses.
That was how the demo was
Not near,
supposed to
not
start.
misses.
Well,
That
I
be
was trying to
crash.
make it a little bit more PC.
Right.
So, what happened here is we executed this job. It sends it up to the server. The server figures out how to distribute this into smaller tasks, which get distributed to the machines in the server. So we have 21, 23 machines. I don't know. Some of them failed the other day. So I started out with 23. Yesterday I had 21. I'm not sure what happened. But as Eric said, fault tolerance is big. So this data was stored on those 23 nodes. 2 failed. Doesn't matter because it redistributed. So this split it up into 432 tasks. You can see at the bottom. Now, if you were running one machine with one core, those tasks would get executed sequentially, and you'd have to wait for every single one of them to finish. As it turns out, we have 92 cores across our cluster that we can work with, so they get executed 92 at a time. Escape out of that. And that finished in, what was that, 51 seconds. So we just did a big spatial join, 17 million across 17 million in 51 seconds.
That's not bad.
Not too bad. And you can see here as it went through all of these distributed tasks. So you do actually get progress. I'm not going to let you talk. This is my demo.
But now I can talk because you stopped talking.
No.
Yep.
Go for it.
Okay. Keep in mind, these are commodity machines that we're running on. Actually, how we were able to do this, we didn't have to go to Jack or anyone like that and say, Mr. Dangerman, can we have $150,000 to buy some really cool blade servers and stuff? What we did was we took flow-down machines to Esri.
We did try it, though.
Yeah.
He said no.
Denied.
Yeah, definitely denied.
But we just took machines, and flow-down machines at Esri in our parlance are machines that developers don't want anymore because they're just so old. You know, when a machine is a few years old, you just get rid of it. Maybe the admins take it, maybe someone else in the organization takes it. But these were machines that they were about to send to the machine shredding machine. It's sort of like this wood chipper thing, but bigger, I think.
It's the one on the right there.
Yeah.
That's our cluster. That's what we're running with.
High quality stuff. We did put a little bit more memory in them, but each of these machines had either 4 or 8 cores in it. But, you know, it's a 5, 7, 8-year-old machine. Nobody wants that, but we do. We take all of Esri's junk machines now.
Every weekend we do a sweep, and we take all the ones that aren't locked down, just throw them in our cluster.
We also like to do grave robbing when people go on vacation. Where's my machines?
I don't know. I didn't do it.
No clue.
Someone took it. Are you done?
Yeah.
Okay. So, we calculated that giant join, and the return of that was about 513 features. So that's the point, right? You had 17 million. It was hard to see what was going on. We got 513 back. That's pretty easy to work with. And as you can see, pretty much what we expected, we find flights that are flying with each other across the Atlantic. So that's pretty cool. So that's one tool down. I've got a whole bunch of demos in whatever order I can.
Did you show the attributes
What?
or anything?
No.
Any attributes?
There's no attributes.
Oh, okay.
It's not a summary.
Oh, okay. Just curious.
Weren't you in our session on Tuesday?
I just want to see what data was there.
Okay, so you can see at each one of these points there's actually 2 features. So this is aircraft ID ACA868, and then this one would be DAL467. So those were 2 planes that were flying basically right next to each other. Within a mile in a minute, I wouldn't say they were too close.
Or maybe they passed by each other going in opposite directions. Okay.
So another thing you can do with this FAA data is another tool that we have that's called Reconstruct Tracks. This is actually a rather interesting tool. It's not something that's in desktop. The only thing that's close to it is there's a point to line, but it doesn't take time into account, and it doesn't do any summarization of attributes. So if we were to take that flight data and look at the tracks, it's actually quite interesting. But it's also chaos. What you get is fireworks. Really cool fireworks as they render. Now these are actually summarized based off of summary statistics that we calculated for each track. So if you think about planes flying through the air, and they've got breadcrumbs as it goes across. And each one of those breadcrumbs has the ground speed and the altitude. And so when we create the track, we actually summarize those attributes. So now you have a track with a start time and end time, a min ground speed, a max ground speed, an average altitude, every summary statistic you can get about the track. And we can change the symbology on this. Right now it's on mean ground speed. We could change it to track duration, so the actual length of the flight. We could change it to the average altitude. We just maintain all of those summary statistics. Oh no, I identified. Okay, good. When you identify with this much data, sometimes it could take a while. So another cool thing you can do with this track data is, I'll turn it off while it's rendering. We can actually say, I only want to keep the tracks that go to, what did we do last time, LAX?
No, let's look at San Diego.
I was going to do DFW. Now we put that back on. Now we see all the flights that are flying into DFW. And you can see all of their flight paths as you zoom in. So pretty cool. That's one thing you can do with it. Now, another use case for the Reconstruct tracks is hurricane tracks. So we have a hurricane data set. It's about 200,000 points. And what it has is the location, the timestamp, the wind speed, and the pressure. And so while we reconstruct those tracks, we're going to maintain those attributes, or those summary statistics. So here's your hurricane tracks. I'll move that out of the way, get more space. Now, because these tracks are temporally enabled, we can actually use our time slider to play back the hurricanes in time. And what you'll notice is that until about 1960, they weren't really tracking anything near the Pacific Ocean over there. And then, boom, there it's all there. So you can go in and you can, what?
No, go ahead.
Do you want to give them your hurricane trivia?
Yeah, who wants to hear some trivia? Yeah, I knew you did.
4 people out of all of them. I think that's a no.
That's a huge yes in my mind.
Okay.
Okay.
I'll bring back all of them.
Okay, bring back all. What? There are 2 crazy things that you can see here on the screen. What stands out? One thing that I thought stood out was the fact that you don't see a hurricane going across the equator. A hurricane or a typhoon will not go across the equator.
This one's getting close.
When they get close, if they do try and cross it, they explode in a huge hydrogen bomb-like thing, okay?
It's true.
They don't go across the equator.
Look it up on YouTube.
The other interesting thing is when you look at all that data, there's one area that's missing hurricanes that you go, why? South Atlantic. There's only been one hurricane in about the past 100, you have like 100 years worth of data? How much data do you have?
Since 1890.
120, 130-ish years, one hurricane in the South Atlantic.
2010.
Why?
It was 4 days long.
Are there any hurricaneologists here that know?
He is.
Why would you say
that's
it?
not good.
Exactly.
You didn't.
You're an expert.
You didn't know that.
I asked someone in a previous session and they told me, so I knew it was cold water.
Was I there?
Yes. Apparently
Whoops.
not paying attention.
No, I was just probably asleep.
Okay, yes, because the water in the South Atlantic's too cold.
For the first one was Coriolis.
Uh-huh, right. It's not hydrogen bombs? Okay.
They don't explode?
That's more exciting.
So everything I saw on YouTube was a lie? Okay. The internet doesn't lie.
No,
He's making
never
stuff
does.
up. I don't
Better
trust
tweet
him.
about that. Give some more good information.
Done with the trivia?
Yeah.
Great. He wins a prize.
Oh.
So another thing we can do with this hurricane data is actually,
Some money over there.
if we look at the attributes, there's a buffer type. So if we say, expression, we can actually type out an expression here that will buffer at each point in the hurricane and actually create the width of the track at that point. And so what you get from that is something that looks like this. Intestines or something, I'm not quite sure. So what we did for this one is we actually buffered by the wind speed. And what you'll notice is that, he's going to correct me, but the wind speed drops dramatically as it hits land. Is that good? Good. I'm not lying to people. So as you can see here, the size of the track decreases as it hits land. You wouldn't be able to see that with any of the regular summary statistics because they only apply to the whole track. This actually applies at each point. And to get an idea of what that looks like here, this is how we're doing it. If this renders, it might not render. So we'll turn off time. We'll zoom out a little bit. I actually have 200,000 buffered points, so that's not surprising that it's not working. But we'll zoom in on this one. That's what we did. We buffered each point. We did a convex hole around each one, created a line, put them together. Boom. There you go.
That's pretty cool.
It is pretty cool.
Nice visualization.
Yeah. Yeah, I'm glad it rendered. Should I keep going?
Yeah.
Okay. One more demo. Another data set that we have that Eric will show you a graphic of what the points look like. You have that for taxis, right?
Yeah.
Like the large scale?
Yeah.
Is taxi data. So we have taxi data from the New York Taxi Commission, and the data set I'm using is for 2013. It's about 170 million points. It's stored as 12 CSVs. Each one of those CSVs is about 2 gigabytes. So that's the type of data we're working with.
If you are looking for a fun data set to play with, since 2009, the New York City Taxicab Commission has been collecting electronic information on every trip. So since 2009, there's approximately 1 billion taxi trips that you can go and download for your very selves and then play with. It's actually startling. You can find all kinds of things that look like fraud and whatnot. You can see when people identify a pickup location, and sometimes pickup locations are before they actually get to the terminal at the airport, kind of sketchy behavior like that.
What are you suggesting?
Fraud. I don't know.
Very blunt. Wow.
You asked a question.
I was expecting
anyway, it's a fun data set to
something.
play with, and it does span, I don't know, 7 to 8 years, something like that. It's a lot of fun to play with.
Yeah, it's a good data set. When it first came out, they only had 2013, and just recently they added the rest of them. So what we have is 170 million points. I've also registered this with my portal, and what I'd like to do is aggregate this into bins. And so we'll do the Aggregate Points tool. So we choose our point layer. Again, this is something that's stored in our big data file share, and it's the taxi data set. It turns out it's the pickup location. So this data set has 2 latitude, longitude. It's got pickup and it's got drop off. So each record is the entire trip. There's no breadcrumbs. Now this Aggregate Points tool, you could aggregate into polygons, which is just summarizing the points into the polygons. But what we want to do is bins. These bins could be square or hexagonal bins. Which one should I do?
Hex.
Hex? Okay. Set our output name.
People like hexes.
They do.
Something about it.
I don't know.
Comes from playing board games as a kid.
Settlers of Catan,
Stuff like that.
Beehive, any number of things. So we'll choose a distance interval. The distance interval defines the height of the hexagon. And if you're using squares, it just defines the side of the square. So we'll say 1 kilometer, give or take. We could set an interval, and what that would be is actually the temporal width of the cell, if that makes sense. So if we said, I actually want to aggregate into bins every month, I would get, for every location, I might get 12 bins that are temporally enabled that I could then play back through the time slider and see how the data changes over that 12-month period. Alternatively, you could create a space-time cube, if any of you are familiar with the space-time cube, and then you can do your emerging hotspots, your anomaly detection. You can find out all kinds of interesting space-time patterns on that data now that we've aggregated it into something that's a manageable size for the desktop product. Because before it was a big set of points, now it's a moderately sized cube. But for us, we're going to return features. And again, we can set our summary fields. So what we'd like to do is maybe the average passenger count and the, let's say, the average trip distance. Call that. And the last thing I want to do is actually filter the extent to only what I'm looking at. So I can set the output extent to the current display extent, and then only the data that's in that display there will get returned. Cross your fingers that this will run. If it doesn't, it's okay. I have a backup. So this one is about 404 tasks. It's less tasks than the join because the spatial join is actually a pretty computationally intensive thing, right? It's not. I wouldn't say it was a Cartesian join of 17 million and 17 million, but it's pretty close. So that's a lot of comparisons. So here you can see it running through. This one should take about a minute, give or take. Anything you want to add while it's going?
May want to talk about the diminishing returns regarding having too big a cluster.
Too big a cluster.
Yeah, not enough data.
Oh, yeah, sure. Okay, I guess. So one of the things that's interesting is the hurricane tracks is only 200,000 points. At our scale, that's not too much. But it's interesting because it takes about as long to process as the FAA data. And the reason is because it only creates 4 tasks, which is severely underutilizing the cluster, but that's just because the data is so small. So when you're working with smaller sizes of data, you may not, it may be unexpected how long it takes to work because it's only distributing across a few cores versus all the cores. Because it doesn't make sense to distribute across all the cores, you may get 4 points on each core. So the number of tasks is highly dependent on the size of the original source data. I think I made my hexagons too big. But we can now summarize these hexagons based on the attributes that we had, which is obviously going to be Manhattan has the most amount. Now something interesting. This is risky. I'm going to open a scene. I don't know if you've seen this one before.
Go for it. Yeah, I did see it.
Okay. This is risky because my laptop has been giving me all kinds of trouble. I'm going to put this in 3D.
Oh, shit. No, that's the liquor
Ah,
talking.
3D. Ooh. No. So what you can do with this is actually something I learned how to do yesterday. It's pretty cool. We can take this and set the height of each one of these bins to something based on the attributes. And that is way too much. So let's do over 2. Okay, either way. But you're going to get some serious, you'll get some ideas on how this scales.
This is like the worst infographic ever.
And it just keeps going up. Over 100? Okay, we'll do that. I don't know if I can get back, though, to the ground. I think we might be out of luck. Can I just zoom to layer? I should be able to do that. Okay, that kind of saved me. So over 100, let's do that. That's a good one. We'll go in. There you go. Much better.
It's a really tall building.
Right?
Yeah.
So it kind of gives you a little bit more
eye candy.
Eye candy, because everyone loves 3D. But it also tells you really how much more is in that one section that's sticking straight up. And so we could symbolize on other things. We can also change this to go based on the
Passenger count. Yeah.
Count passenger count? Is that what I did? That won't work.
Mm.
I put in the wrong statistic.
Oh.
It's the same as count. And we'll take this and we'll multiply it maybe by 100. There you go. So this one doesn't really have quite the same patterns, but Now we actually have a visualization that shows two things, the average passenger count, and because we symbolize based on the number of points, you get that as well. Whew, that worked.
Pretty good. You're on
Yeah,
a roll.
actually it didn't work right before.
Really?
Yeah. Yeah, my computer has had any number. Let me show you guys something, actually. You haven't seen this, but this is what happened last night while I was trying to figure out what was going on. So if you'll notice, this is not the demo that I was trying to show, but I spent about an hour doing this.
That's horrible.
It was fun.
Jeez, that's the worst.
It's your turn.
Okay.
I'm done.
Okay, those were good demos. I like this.
I'm done for the week, actually.
Nice.
Yeah.
Oh, jeez. Let's see if this thing's going to work again. Oh, good. Okay. Let's see. So let's go into a little bit more detail regarding what actually is taking place, how some of these, what are some of the algorithms and visualizations of them. Let's talk in a little bit more detail about what's going on here. First, the operators we have for aggregation and summarizations, one of the tools will do a spatial join where moving left to right, you see your target features, which happen to be in this graphic polygons. You have some join features, which are points, and then it will actually go and compute the summary statistics or do whatever operation you want, and then prepare a new resulting data set that has been colored or has the information applied from the joined features, okay? That'll have the geometry of the target features. You can do space-time slices, or what we refer to as panel data. Here we're taking just spatial data, spatial polygons, and we have a collection of spatiotemporal points you can see in the vertical dimension with the older things being at the bottom, the newer things being higher up, the now and then that you see on that vertical axis. Then you can apply filters, temporal filters, to control what constitutes a valid time range for creation of this panel data. And so then you see on the right, you see the summary data where you have the original polygon geometries, but the resulting polygons are also temporally aware. And why you would do that is so that then you can use your time slider to start to see how things are changing, maybe on a daily or hourly, weekly, monthly, whatever basis, okay? You can use those temporally aware polygons with time sliders so that you can see how things change with time. Your data sets, you can take your lightning strike. This is just some lightning strike data, a couple weeks worth. And here we just aggregated it or summarized it into bins. You can also summarize it into hexes, as Mike showed you during the demos. And you can also summarize it into polygons. This right here, this actually is probably US counties, okay? So you can summarize this point information 3 different ways. Aggregate it or summarize it. Let's see. Now, an interesting thing you can do is when you do this, you can also take into account the intervals like we did when we talked about the panel data. Here we did it with 6-hour intervals with the grid cells. So this is over a couple weeks. Each one is a 6-hour interval. You can do that with grid cells. You can do it with hexes. And you can also do it with polygons, here, counties. Create panel data out of any of this stuff. Now, let's talk a little bit about time slicing. When you want to define a time slice, there are 3 parameters that you need to take into consideration. It sounds complex, but actually it's pretty simple. And this is actually a really nice graphic displaying it. So you see time moving along the horizontal axis with the older stuff to the left, the newer stuff or current time on the right. One thing you need to do is you need to look at the interval, essentially the duration of the time slice. That's represented across the temporal spectrum as these brown or grayish, brownish regions, okay? Those are constituting little intervals, all the same size intervals, but they're a sequence of intervals. You then define a step, which is essentially the frequency of each of these slices. And here the purple represents the step, as perhaps that's a day. Maybe the interval is 18 hours, okay? Think of it that way. Then finally, you have a reference time that you use for aligning all these different intervals and steps, okay? So these are the 3 things that you need. You need an interval, step, and reference time. Now, here, suppose we had some data represented on the temporal axis as those little red points. If we were then aggregating them using this time slicing, you would see in the first interval there's one red thing that occurs during that. In the second interval there are 2, third interval 0, fourth interval 0, and in the fifth interval 1 red item. Okay? That's how you would aggregate with time slicing, or a representation of it. Now, if you want to do hourly slices, just set your interval to be 1 hour. If you want to have a 1 hour interval every 12th hour, you'd set your interval to 1 hour and your step to 12 hours. If you want to summarize your data into every Monday, you would set your interval to be 1 day, you'd set your step to be 1 week, and you'd set your reference time to be some Monday. Okay? It's not too hard. I think everyone can understand that. Now, let's talk about spatiotemporal joints, a little bit different from the spatial joints that we showed earlier. Here we have target features that are spatiotemporally aware polygons being joined to spatiotemporally aware join features, and on the result on the right side, you see, of course, spatiotemporal polygons. Now, if we go and we reverse what constitutes the target and what constitutes the join features, you see the result on the right. Okay? That's how you can get, by changing the order of what's the target and what's the join, you can get different result geometries. You can do, of course, aggregating points into bins. We saw that earlier. And if you have spatiotemporally aware points and then you specify an interval, you can get essentially your space-time cube. That's shown in the big pile of that really large Rubik's Cube. Actually, they do make a 5 by 5 by 5 Rubik's Cube.
I'm sure you solved it.
No. Just tear them apart. Let's see, reconstruct tracks. Suppose we have spatiotemporally aware points. This is observational data. Maybe these are, that airplane that's flying through space and time and you get an observation every minute. Or maybe it's a delivery truck in your organization and you're having, or buses, and you're having it every minute or every 10 seconds report its position. You're getting observational data. All that observational data, you have many observations that are tied to one feature. So if there is an identifier associated with each of these observational points, you can then reconstruct tracks. That's what Mike was doing with the hurricane data. Each of those hurricane observations had a hurricane identifier, but different location in space-time. So that's one of the tools that will allow you to do that. Here, again, just the raw hurricane data, a little bit of it. You can reconstruct it like this, and okay, maybe it's colored by vertex count, something like that. And then, of course, as Mike showed, you can then also buffer that based upon things like wind speed, for example. So just different ways to visualize your data, observational data. Okay, let's talk a little bit about performance here. People are always curious, so let's talk about it. Here this was at one point when our little cluster of those machines you saw piled up in that picture that Mike showed you. At one point we had 16 machines, and these were 4-core machines. These were relatively old ones, and we outfit them each with 14 gigabytes of RAM. 14 gigs was available, and we ran with a test data set, 2 test data sets. One was, again, the New York City taxicab data, which was 170 million pickup points. And then we also had a collection of polygons representing every block from Census Tiger data in the New York City area, which is 40,000 of those. There are 40,000 blocks in New York City. Now, if we go and look at the taxi pickup points, that's what you see. Not very useful information when you just draw it. What's equally disturbing is you see taxis that are picking up people in the Atlantic Ocean or Long Island Sound or the Hudson River. That's one of the interesting things about big data. A lot of it's junk data, So you have to be prepared to understand that some of your data is just going to be complete junk like this. Now, if you go and zoom in, this is very dense data. Here we're zoomed into Grand Central Station inside New York City, looking at a corner of Grand Central Station. That's 100 meter by 100 meter extent. Each of those little blue dots is one or more pickup locations. So this is very dense data. And you can go grab it yourself. This is really fun data to play with. Just don't use it with traditional processing techniques. And don't try to paint it to the screen. It'll take a long time. Now, here's some experiments we ran. We looked at this cluster. We looked at the time to compute buffers, the time to do aggregate by cell, and the time to do aggregate by polygon. And okay, you see things going on the horizontal axis. You have the number of cores that are being applied with a doubling at each thing. It goes from 1, 2, 4, 8, 16, 32, 64. And in the vertical, you have processing time in minutes for this particular cluster configuration with this particular collection of data. Now, why do you care? That's just number. Okay, you're showing me curves, and they're all kind of curving the way you'd expect. Well, think of it this way. If you were running this buffer operation on a standard desktop using the standard buffer GP tool, that's equivalent to running one node in this cluster. And here you can see running the buffer would take, maybe 53 minutes if it completes. Or doing aggregate by cell would take 24 minutes. Or doing an aggregate by polygon, 44 minutes. That's what you can do today, okay, with standard processing. Now, if you just took your machine that had 4 cores on it, say your cluster only had one machine. Your cluster has one machine. You're still running big data analytics. But I'm taking advantage of all 4 cores. So the time goes from 52 minutes down to 12 minutes, or from 24 minutes down to 6 minutes, or 45, 44 minutes down to 11 minutes. That's just one node in a cluster. And that's only a 4-core machine. Now, if you have 4 CPUs, each with 4 cores, that's the equivalent of 16 cores. You can see how much faster it gets. And finally, if you use all 16 machines, you get the number on the right. Okay? So that's good. You see scaling nicely. Now, we threw an even bigger test at it. Same machine. We created a data set that had 4 billion points. And we wanted to aggregate those 4 billion points into polygons. So we said, let's just take the US states polygons, of which there are 52, with DC and Puerto Rico. This is Tiger data, okay? Anyway, to aggregate the 4 billion points into the Tiger states geometries, you get 12 minutes. Get that done in 12 minutes. That's pretty good. 4 billion points into 52 polygons in 12 minutes. We then took every single census block in the US, which there are 11.2 million census blocks in the US, aggregated into those, and that operation took a little bit more than an hour and 10 minutes or so, something like that. So that's pretty fast. 4 billion cross 11.2 million in a little over an hour with a 16-node flow-down machine cluster. Now, you saw during the plenary, Suzanne Floss, she gave a demo that was talking about fraud detection. Remember that, the banking fraud? Where she said, we have 1 billion bank transactions. We have an origin location, a destination, and some other metadata associated with it. Well, in order to provide the processing for that demo, the group went and configured an 18-node cluster, but with a little bit better machines. There were better hardware available. There were 8 cores per node rather than 4, and a little bit more memory, 24 gigs of RAM. So 18 nodes of reasonable machines.
That was a good weekend of taking computers. Oh, I don't have my mic. Sorry, you guys can't hear me.
Oh, I can hear
I'm
you.
just telling jokes.
Okay.
I said that was a good weekend of scavenging.
Yep.
To get that clustered.
Very effective. So then, in order to do that, ran essentially did a spatiotemporal attribute join of those billion points, joined 1 billion points against itself, where what we were looking for was a 1 kilometer radius, a 1 hour time window, where the transactions are all going to the same bank. That's a little bit like the FAA thing that Mike was showing. Spatiotemporal attribute join. And that operation, we were able to complete in less than an hour of processing on that cluster. And that includes all the I/O going to the spatiotemporal data store, the thing that's sitting on top of Elasticsearch. So that's pretty good. 1 billion cross 1 billion in less than an hour with a reasonable collection of desktop machines. So we were pretty happy about that. And I think that's pretty good performance. Actually, it was closer to what you said, 40 minutes rather than 50.
Yeah, it was about 40 minutes.
That's really fast.
Yeah.
Okay, so let's conclude this thing, and then we can take a few questions. Why would you want to consider using all this big data, geoanalytics stuff inside your organization? First, of course, it lets you get big jobs done faster. Some of the jobs that Mike was doing are actually very difficult today with just standard desktop. He was able to demo them in front of you and get these operations done in a minute's time. Makes it big data easier to use, easier to share. Everything we showed you was just GP tools. You didn't have to learn any exotic programming language. You didn't have to do functional programming. You didn't have to learn anything at all about distributed processing infrastructures. You just used some special new GP tools, and you made it point at your cluster. So much easier to use, easier to share. All that stuff that you saw, like Mike was doing, is published as a WebGIS layer inside your portal. So other people can then look at what you did. Look at your pictures of the hurricane worms and stuff like that. It parallelizes the processing and focuses on both space and time, spatio and temporal analysis for massive dataset processing. All the stuff is out of the box and ready to use. You don't have to publish anything, and it has familiar and simple interfaces. It works with Pro. It works with the Portal Web UX. It works with Insights. It works with Python notebooks. It has a REST API. You can script it in raw Python. These are all things that you guys know how to do, okay? Very familiar, very simple interfaces. It allows you to do faster prototyping, raw R&D, geeking around, making crazy maps, and getting insights into your collections of data. So basically, lets you see your big data picture in a clearer and more meaningful way. Okay? That's geoanalytics. Any questions?
What software is required for each of those and licenses?
You're asking productization questions. It's basically, we talked about it a little bit earlier. You're going to be laying down Portal, okay? You have your server and your Portal, and it's also an extension. It's an extension to server, okay? So it'll be one of those extension things, much like GeoEvent.
So for each node, you need an extra license of Portal, is that correct?
I think there's some kind of licensing like that. You're going to have to talk to product people. Yeah.
Just putting Portal with an extension.
Yeah. Do you want to know how much it costs? Don't ask us.
We'll figure that out later.
We're selling it on Craigslist, so if you want to get the better deal.
We're just developers. We don't know that stuff. Don't know, don't care.
That's great. That's good. Good answer.
We'll just torment you a little more. Any other questions?
So, in one of the slides you showed that connect user-managed databases. So something like Teradata, it's just going to consume the data out of there, but when it does, like the distributed processing, it still has to go onto your cluster.
Correct. Other questions?
Are there already configured clusters available for rent? Like if you add data, you said, please process this for us.
Craigslist. No, there aren't. We don't. It's not something we're selling with ArcGIS Online or anything like that right now.
So you just go and find someone with the cluster set up and you just ask them to process your data.
You could do that.
That's what I'm asking. Someone that has a cluster already set up, the licenses, say we have a bunch of data, please, we want to process. We want access to your cluster for this kind of time.
Or you could do something through Amazon as well, through AMIs. I mean, you can load up server onto Amazon, and you can load this entire stack up onto Amazon if you wanted to use it for a short period of time. That's probably what you'd want to do.
And your big data file share could also be an S3.
Yeah.
They would be just any licensing process.
Yeah.
Right.
That's right.
Right.
Yeah, that's right. Other questions? Yeah.
Spatial temporal join is fantastic, but is there any way to have that on the desktop for smaller data sets?
Not at this time. I would not say never. I think it's going to be interesting to see how this technology evolves. Technically, there's no reason why it couldn't, and we have done that before, but it's all a productization thing right now, okay? So it works with Portal right now. In the future, you'll have more capabilities. It'll just start growing. This is our initial release, okay? So based upon your feedback to your representative or whoever you talk to at ESRI, start pushing them and say, hey, this is cool, but I want something else, something a little different. How can you accommodate me? Okay? Because our development agenda is driven based upon what you guys want. Okay? So if there are things that you like about the story or things that you wish the story was slightly different, talk to the people that you normally do and let them know, okay? I would really encourage you to do that because technically we can do all kinds of crazy things. It's just we have to prioritize, and our prioritization is based upon what you guys say, okay? Any other questions? Wow, quite crowded. Anyway, enjoy your party tonight. Looks like it's getting a little prettier outside, a little bit of sun and all that. So thank you very much for coming. We'll see you later.